Okay, this is the last section in chapter 1, and we're not going to concern ourselves with all of it, but part of it we should take a look. So what we've been doing is called, we've been working in the Cartesian coordinate system. So that's the typical system that we always use. We have X, Y, and Z axes, but we want to have different set of axes now. Basically, that means we want to express everything in it with a different set of variables. Instead of X and Y, something else. So if we have a point in the XY coordinate system, we can also, so of course we can say the coordinate, to locate the point we can say the coordinates, we can give the X and Y coordinate. But we can also use a different way of locating the point, and that is we can say how far is it from the origin. But if we just said how far it's from the origin, every point on like a circle is going to be that far from the origin. So we have to say a little bit more than that. So we also say the angle that it makes with this axis. So we'll talk about that angle and the distance, or how far it is from the origin. And those two together will uniquely identify a point. If I tell you the angle is 45 degrees and the radius, or the distance from the origin, is 2 units, then there's only one point there. So when we do it that way, when we identify a point using those two quantities, that's called using polar coordinates. And so one thing we'd like to do is figure out what's the relationship between the polar coordinates and the XY coordinates, because obviously there's some relationship. For example, it's easy to realize that there's a relationship between the distance it is from the origin and the XY coordinates, because the Pythagorean theorem says that this distance that it is from the origin is related to, this is the Y coordinate, this is Y, this length is Y, and this length is X. So obviously X squared plus Y squared equals the distance squared. So there's a relationship between the radius, we usually call it the radius, or the distance from the origin, and the X and Y coordinates. And then there's also a relationship between this angle and the X and Y coordinates, as you certainly know from geometry. So here we say, this is that, so here's a point, there's the distance, and there's the angle. And this could be like the polar coordinate system. So we have many different distances, and many different angles, and we have all the different possible, possible radii. So she says every point except the origin lies on exactly one circle and one such ray. Right? So here's a point. It lies on just one of the circles and one of the rays. And of course, they say that the theta is measured as opening counterclockwise. Of course, that's true, right? Like that. And then she also says it also makes good sense to require that theta be between 0 and 2 pi. Of course, we could have bigger angles than that going around and around, but then if we allowed that, then we would have to give multiple coordinates for a single point. I mean, we could give multiple coordinates. So I could say this is 45 degrees, but I could also say that so I would say the coordinates are r comma theta, but it's also r comma theta plus 2 pi and theta plus 4 pi. And so we'd have many different sets of coordinates for that one point. We don't really want to have that, so we're going to always insist that theta be between 0 and 2 pi. She then says, though, occasionally, however, it's not useful to restrict r to be between is not to be a non-negative, to be non-negative. And even theta to be between 0 and 2 pi. In that case, no point of R2 will be described by a unique pair of polar coordinates. So you could have this as many other sets of coordinates, because n can be any integer, or you could also use negative r. So you could talk about this point having coordinate r, and then theta is all the way over here, or you could say negative r, and theta is just this amount of theta, or this amount of theta. So here are some sample coordinates. So here's length, radius of 1, or actually, I guess it's negative 1. And, oh, sorry, let's go here. Distance is 2, and this is pi over 6. So what is pi over 6? Well, pi is 180, so pi over 6 is 1/6 of 180, or 30 degrees, so I guess that's a 30-degree angle. And then here's another point, 2 and 5/6 pi, so that's 5 times 30, or 150 degrees, and so on. So now we have these variables. Instead of x and y, we have r and theta. So we can say, just like normally we would write something like y is some function of x, now we could try r is some function of theta, because these are the new variables involved. So r is some function of theta. So here's an r as a function of theta. So we, just like we might ask, what's the graph of this look like? We could ask, what's the graph of this look like? So how do we do that? We just put in different theta and figure out what the r is. So for example, if we put in theta equals 0, cosine of 0 is 1. So r equals 6. So when theta is 0, r is equal to 6, which means that this point is on the graph of this curve. Okay, then we could put in other things for theta. For example, we could put pi over 2. So when we put pi over 2 for theta, we know that that's 0, so it's 6 times 0. So r is 0. So when the angle, so we have pi over 2, 0. Well, 0 is always, radius 0 means we're always here. So that's a little confusing because we don't know exactly how we got there. So we need a few more points like this one or this one. So let's try pi over 4. So when we put in pi over 4 into cosine, we get 1 over the square root of 2. So that gives us, or it's also, so it's 1 over the square root of 2, but it's also the square root of 2 over 2. That's another way to write the same thing. So if we multiply that times 6, we get 3 square root of 2. So pi over 4, and then the radius is 3 square root of 2. So here's pi, this angle here is pi over 4, I guess. I guess that's supposed to be a 45-degree angle. And then this radius for there is 3 square root of 2. So we get to this, we have this point. We said we have this one, but that's a little unclear how we got there. But anyway, and if you put in pi over 6, apparently you'd get this length. So that would put you here. So somehow it looks like we might be getting a circle. Okay, so maybe we do get this circle. And you can read a little bit more about that here. So the basic conversions are, so we saw that this one was, we saw that one, and the tangent of theta is y over x. We know that the tangent is sine over cosine, and that's sine is just y and x. we get this relationship as well. So this is r and tangent of theta in terms of x and y. And then we can also do x and y in terms of r and theta. So if here's y, and this is r, y is equal to r times the sine of theta. And we also have this one. So we have these easy relationships. We start out with polar and go to Cartesian, or we start out with Cartesian and go to polar. So these are very useful when we want to translate from one system to the other, and they're not hard to figure out. So then she says here in example 3, she says we can use formulas 1 and 2 here to prove that we actually get this picture, which is a circle centered at 3, I guess. 3, 0. So she says we start with this. It requires a little bit of ingenuity to convert it to the corresponding Cartesian equation. The trick is to multiply both sides of the equation by r. So when we do that, we started with this equation, multiply by r, I guess we get this. Now 1 and 2 immediately give. R squared is here, r cosine is x, so we get this is x squared plus y squared equals 6x. Now they say we can complete the square. X minus 3 squared plus y squared equals 9. And that tells us this is centered at 3. And it's a circle of radius 3. Okay, which is what the picture shows. Yeah. There's a little bit of ingenuity there, a little clever ideas. But anyway, we have shown it. Okay, next thing is what they're called. So this system is called polar coordinates. Polar coordinates. So that's when we're working in the plane, only in the plane, not in 3D, and we use r and theta as our coordinates. And then we can, as we saw, we can write equations that relate r and theta and wonder, for example, how to graph them. What if we're talking about 3 dimensions? So 3 dimensions, we can take the x and y and use the polar coordinates, and then just use, for the 3rd dimension, we can still use z. They say that's one way to work with 3 dimensions and with a different coordinate system. Actually, we're still using z, but we're in the xy plane, we're not using x and y, we're using r and theta. So the cylindrical coordinate, and she says, because there are other ways to do this besides using z, but one way is to use z. So she calls it a naive way of generalizing from polar to 3 dimensions. So these are called cylindrical coordinates, and then we would have r, theta, and z. And then we have to say, how do we convert from Cartesian, from cylindrical to Cartesian and vice versa? But of course the z is the same in both, so we don't really have to do anything new. We just have the same stuff that we had before here, and then we just have z equals z. And we can also make this same kinds of restrictions on r and theta, although I guess we don't have to do it, but typically we would do that. And then we could have a unique set of cylindrical coordinates. And let's see, a point on the z-axis will have 0, 0 for r and theta, and then some value for the 3rd coordinate, so that we can move along the z-axis. And she says this coordinate system, cylindrical coordinates, are useful for studying objects possessing an axis of symmetry. So like if we have a cylinder, we might want to write the equation for it using cylindrical coordinates instead of trying to do it with x, y, and z coordinates. So then we can also note that r equals r0. The surface is a cylinder centered at the origin. I guess that's what this is a picture of. a cylinder centered at the origin, centered around the z-axis and of radius r0. Because if we fix r, but let everything else have flexibility, then we can achieve any point on this cylinder which is centered around the z-axis and has radius r0. The surface theta equals theta sub 0, some fixed theta. That will mean we're taking this, but the r can be anything. So I guess it would be like a plane that goes through here and at some particular theta. So it's a vertical plane containing the z-axis, or half a plane if we keep r positive or non-negative. Okay, now what about this? So this is a horizontal plane because we allow r and theta to be anything, but we restrict it to just a particular height. So that's going to give us a horizontal plane. So in this example, they say, suppose we're working in cylindrical coordinates, so we're working in 3D, but we have this equation. So what does it look like? Well, we already know what this looks like in 2D. It's that circle. And now all we do is we let, this does not have any z in it. So that means z can be anything. So we get this cylinder, but centered here, instead of centered around the z-axis. Okay, here's another one. Suppose we have this, z equals 2r, but we're talking about cylindrical, so theta is not mentioned. That means theta is free to be anything. So it turns out to look like this, and you can read through this to see that. The next thing is spherical coordinates, and that's also in R3, but it's a different way of doing it. So in, let's see, the picture is like this. So we have theta, the same as before. We have r, but it's a different r, or it's not even r, it's rho, but it's the distance from the point to the origin. Now that's not what r was, because before, if we had this point, what would r be? It wasn't the distance from here to here. It was, the r was only in the two-dimensional plane, so we had to go sort of drop down to here and say, what's the distance from here to here? That was the r. Then we said z would take us up to here. So this is the actual, when we're talking about 3 dimensions, this is the distance from the point to the, from the origin to the point. So r actually is not the distance. We didn't notice that before, but r is actually not the distance when we're talking about 3 dimensions and the cylindrical coordinates and r. Anyway, this is the distance. So theta is, okay, what is theta? So if we have the point, we want to figure out what theta is. So theta is if you drop down to the plane and then draw a line back to the center, that's theta. That's kind of what you might expect. We don't care about this r here. We don't record that. But we do record this here. That's the length from here to here. So that tells you basically how far to the meridian here. And then we have one more angle, and that's the angle from this radius line to the z-axis. So that's phi. That's pronounced phi. So kind of a bit more confusing than the cylindrical system. But it does work, right? Once I tell you that rho, this is rho, is say 2, that doesn't uniquely identify the point, right? Because we could have a lot. That would be actually rho equals 2 is anything on this sphere. That's not good enough. So then if I tell you, okay, if you drop down to here, the angle from this point, you drop down to here, and then draw this line to the origin, if I tell you that angle is something like pi or pi over 2 or something, does that nail it down? No, because then you could be anywhere from here down, 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 anywhere on this meridian, right? Okay, so that doesn't nail it down. So then we have to say, well, what's the angle from here to here? That finally nails it down. So that is a legitimate coordinate system. And the symbols again are theta, rho, and phi. And theta is supposed to be, generally we restrict rho to be greater than or equal to 0, phi to be between 0 and pi, and theta to be between 0 and 2 pi. So you can sort of figure out why we need to do that. Then we can talk about equations using, and then we have to do this. We have to figure out what's the relationship between all these and x, y, and z. So that takes a little bit of geometry to figure this out. And then we can take an equation with these variables and then ask, what does it look like? So here anyway, this is the cylindrical equation z equals 2r, which we saw in example 5, converts via these things, these, to the spherical equation. By the way, these are called the spherical coordinate system. So we had the polar, we had the cylindrical, and now we have the spherical. So it converts to this. So this also defines a cone. I guess that was this one that we didn't bother doing, but this one here. Okay, this is the last part of chapter 1. So we know that we have what we call the standard basis for the Cartesian coordinate system, and that's I, j, and k. And we want to develop something similar, but using the new coordinate systems that we've talked about. By something similar, we mean that we want to seek mutually orthogonal unit vectors that point in the directions of the increasing coordinate values. Just like we had for x, y, and z, we want to do the same thing. So first we'll talk about it for cylindrical coordinates. And as you recall, here's a little r, here's a little theta, here's a little z. Those were the coordinates in the cylindrical coordinate system. So we want to get an E, which is in the direction of r. So E means a unit vector, just like I meant. So E is a general term for I, j, and k. So we could, instead of writing I, we could call I E sub x. Instead of writing j, we could call j E sub y. Instead of writing k, we could call k E sub z. So E is just a general term for the unit basis vectors. So anyway, what we want is E sub r, E sub theta, and E sub z. And we want these to be mutually orthogonal and unit vectors. And we want them to point in the directions of increasing r, increasing theta, and increasing z. And she says there's one important difference between the standard basis vectors in the Cartesian system and in the cylindrical coordinate system. In the case of I, j, and k, they don't vary. Their direction doesn't vary from point to point. So if we take a point, suppose we have this point here, and if we ask what direction should we go to increase, let's say this is the x direction, the y direction, and the z direction. So if we want to increase in the x direction, then we should go this way. If we wanted to increase in the y direction, we should go this way. If we want to increase in the z direction, we should go this way. And it doesn't matter what point we move to, these will be the same. Remember, this vector is the same as this vector, right? We said we can translate vectors to a different place. So these are pointing in the same direction, no matter which point we start at. To increase x, we go in the same direction as we would if we wanted to increase x if we started at the origin. However, that's not going to be the case with these. So let's say at this point here, we could say, okay, what direction do we go in order to increase z? Well, that's obvious. We just go straight up. What direction, though, do we go if we want to increase in the r direction? Remember, this is the r direction. So in the r direction, so it's here. But of course, if we were at this point over here, then it would be like that, right? It wouldn't be the same direction. So it depends. So now the direction of increase in r depends on where we are. It doesn't depend. The increase in z does not depend on where we are, but the increase in r does. And so does the increase in theta. So anyway, at this point, this would be the direction of increase in r, this would be the direction of increase in theta, and this would be the direction of increase in z. So those are vectors in the proper directions that we want, but the only thing is we want to make sure that their lengths are the unit lengths, or length 1, just as the lengths of I, j, and k are 1. Well, actually, yeah, right. So first she points out that EZ is actually the same as K. We don't have to do anything about that. And vector ER must point radially outward from the z-axis. That's what we said here. And we also pointed out that it would look different over here. So if we want to write this in terms of x, y, and z, we would say that R is xi plus yz. So if, for example, if we're at this point, then the radial direction, so the x-coordinate of this point is 0, and the radial direction will just be in the y, along the y-axis. If we were here, then the radial direction would be this way, which would be in the x direction, and then y would be 0. So this is an expression for the radial, for a radially directed vector. But we want this to be normalized. We want it to be unit length. So that means we want to divide it by its length. And we know that the norm of this is going to be x squared plus y squared and the square root. You could take the dot product of this with itself and then take the square root, and this is what you get. So now we know what EZ is. It's the same as the z vector itself. And we know it, now we know what ER is. So we need E theta to be perpendicular. So we can use the cross product. We can say E theta is just EZ cross ER. And we could have, actually we could reverse it. We could say it's ER versus EZ. She says the reason for this choice of cross product as opposed to this one is so that theta points in the direction of increasing theta. Well, we could have it pointing in the opposite direction, but we're going to do it this way. To take the cross product, we have to take this cross EZ. So we want to get E theta, we're going to compute EZ cross ER. Now, if you remember back in our chapter, I think it was section 1.5, we had some rule, some formula for calculating cross products in terms of their coefficients. So here it is. So we want to calculate EZ cross ER. So this is it's a cross product that we can say of some A and some B, EZ and ER. So where A has these coefficients or coordinates, A1, A2, A3, and B has these. So for our particular EZ and ER, EZ, this coordinate will be 0, this coordinate will be 0, and this coordinate will be 1. And for ER, we said that this is ER, so let's just take the numerator. We can just work with the numerator. X is the first coordinate, Y is the second coordinate, and K coordinate is 0. So for ER, The first coordinate is x, the second coordinate is y, and this is 0. Okay, now we want to take the cross product, and this is the formula for the cross product, or this is the formula for the cross product here, the second line. So it's A2B3 minus A3B2. So that gives us A2 is 0. So we put it this whole term is going to be 0. And this A3 is 1 and B2 is y. So that's going to give us minus y here. Minus y. And that's going to be minus y times I. And this is going to be A3 is 1 and B1 is x. So it's going to be 1x. This is going to be 0. This is going to be 0. And this is going to be 0. So we end up with minus y plus x. So we get minus y plus x. And then this is on the bottom. Okay, so now we have an expression for not just EZ and ER, but also E theta. So these are our standard unit basis vectors for the cylindrical coordinate system. And they are given here, but this can also be written like cosine theta plus sine I plus sine theta j. Because, for example, this x over this is x over r, and that's the cosine of theta. And this one is y over this, this is r. The square root of this is r. So this is y over r, but that's the sine of theta. So we can write it like this, but we can also it's probably easier to remember it like this. So the standard basis in the r direction, standard unit basis in the r direction is cosine theta I plus sine theta j. And this one is minus sine theta plus cosine theta. Sorry, minus sine theta I plus cosine theta j. And this one is just k. Okay, I will let you go through the one for spherical coordinates. We have this picture here, and it turns out that we get these results. So we can do it this way, or we can express it this way. We can express this one like this, or like this, and this one like this. Okay, in this case, remember, we don't have, for cylindrical coordinates, there was one that we really didn't have to do anything with, and that was the z direction. But when we're talking about spherical, we have to work on all three of them. We do still use the trick, though, of using a cross product. So we get two of them, and then we use the cross product to get the third one. Okay, the next part we're not going to do, but just to say what it is, there's a way to provide a set of coordinates for Rn that generalizes spherical coordinates on R3. So we're going to have spherical coordinate system, so to speak, but in Rn. So it's a generalization of R3. But we're not going to go through that. I don't think we won't need that in our course. I don't know if you'll need that. You can always